So now we're on to some pretty fun, deep stuff here. So in the last video, we looked at the Gibbs energy. We defined the Gibbs energy as enthalpy minus Ts. We looked at changes in delta G, so our changes in G, so that is equal to delta H minus T delta S under constant temperature conditions. And we said that the condition for spontaneity was essentially G's got to go down. All right, so now we're ready to do some fun stuff. So I'm going to plot the Gibbs energy, and I'm going to imagine the reaction proceeding from left to right. So this is the reaction coordinate. We'll talk about this in physical chemistry a little bit more. So let's write down a particular chemical reaction. So maybe we can look at the reaction nitrogen plus hydrogen, the famous Haber reaction here, where it makes ammonia that feeds a good fraction of the world. So without this ability to fix nitrogen from the air and convert it into a form that we can ultimately oxidize up to make fertilizer, most of us would probably be dead. All right, if we look at the left-hand side, that is the side that is nitrogen and hydrogen. If we look at the right-hand side of reaction coordinate or reaction progress, that is the side that is essentially just ammonia. And we can plot the Gibbs energy as we go from all reactants to all products. And most reactions, actually, I think I'm fairly able to say all reactions do something like this. All reactions do something like this, whereby the Gibbs energy decreases as you go from left to right, and then it bottoms out, and then it increases as you go further off to the right. So we might ask ourselves, what is this telling us? So imagine this was a ball rolling down the hill. If you started over at the left-hand side, we would roll down this way. So actually, whenever the Gibbs energy decreases, that is a spontaneous process. So if we start with pure reactants, if we start with pure nitrogen and hydrogen, they will start to form some ammonia. They will bottom out at this point here. This point here is, can you guess? Yeah, it's the equilibrium point. Now, if you go too far to the right, what you find is that you are increasing in Gibbs energy. So it is non-spontaneous to go up the hill, which just means it's spontaneous to fall down the hill. So if you go too far, if you go past equilibrium, you just have to go back in the opposite direction. If you calculate delta G at any of these points, they is actually equal to the slope of the curve. So delta G over here would be positive. We interpret that as being non-spontaneous, which is to say it's actually spontaneous backwards. Whereas over here at the start, delta G is negative, right? So it's less than 0, and we interpret that as being spontaneous. And at the bottom, the slope is exactly equal to 0, so delta G is 0, and that's our condition for equilibrium. Now, in terms of reaction quotients, this is the point where Q and K are identical, and over here, Q would actually be bigger than K, and over on this side, Q would be smaller than K. So that's the tie-in with the earlier stuff we did. And in fact, we'll see later on that there's actually a relationship between Q and K and delta G standard, so stay tuned.